Today we're going to look at solving polynomial functions. Before we do that, let's kind of go back and review a little bit some factoring that we've done in the past. What they want us to do on these first ones on your note sheet is do some factoring. Anytime you're factoring and you have a coefficient or number in front of your x squared terms on one of these quadratics, what we want to do is multiply together both this number in front and the last number, in this case, negative 30, and see what's going to multiply to that number and also add to negative 7. And if we think about this a little bit, I think we can come up with that negative 10 times 3 is going to work out for us here. Now, that doesn't mean our answer is going to be x minus 10 times x plus 3, because if we multiply that together, that does not equal what we had here. What we have to do with that is factor by grouping. So anytime there's a number in front, like again we have here, we're going to split this middle term up into these two factors we came up with, negative 10x plus 3x. That's the same as negative 7x. So we haven't changed our expression, we've just changed the value, we've just changed the way it looks. Now we're going to group together these two, and we're going to group together these two and find the greatest common factor to do factor by grouping. So in this first parentheses, we can factor out, looks like a 2x. What's left over is x. If we divide the first one by 2x, if we divide negative 10x by 2x, we get 5. Now we do the same thing on the next parentheses. In the second one, looks like both of these are divisible by 3. So if we factor out a 3, what's left is x minus 5. Now, if we factor out this common x minus 5 that we see 2 times here, if we factor that out, what's left over is going to be 2x plus 3. Basically, what's left outside the parentheses here is our other factor. And that now is how you factor that one. If we multiply that back together, we will get what we started with. That's called factor by grouping. All right, on the next one, we want to factor here too. Now this is not a quadratic. This looks like one we want to factor out the greatest common factor. So what is the greatest common factor here? Look for those numbers and variables that we could divide out. It looks like number-wise, both of these are divisible by 5. So we want to factor out a 5. Now find the biggest amount of a's and b's we can take out. The biggest number of a's looks like a squared, and the biggest number of b's looks like b to the 5th power. So now what's left over in each one when we divide? Well, if we divide the first one, we're going to have 5a left over. B's would all be gone. And in the second one, if we divide by 5, we get 3b. And that would be the answer. It's called greatest common factor. Always check to see, is there a greatest common factor first, if possible. All right, the last one. This one is one we're going to be talking about again today. This is one of those quadratics, but that middle term's missing. It's kind of like plus 0x minus 81. So what's going to multiply to negative 81 and add to 0? Well, in this case, looks like positive 9 and negative 9. So it'd be x plus 9 times x minus 9. All right, so just kind of in general, whenever you're doing factoring, always take out the greatest common factor first, if there is one. If there's a greatest common factor, factor that out first, and then anything else, factor after that. Okay, this last one we just looked at, we're going to be talking about this one more today. There's a name for these types of factoring ones. That is called a difference of two squares. Anytime you have a factoring one where both the first and last thing are perfect squares, it's always going to factor and look like this: a plus b times a minus b. It's called difference of two squares. And we had that in this one. The two things that were being squared were x and 9. 9 was being squared here, and x was being squared. So then it ends up being x plus 9 times x minus 9. Okay, we've seen that one before. The other two we're going to be looking at are new. They're called sum of two squares. Anytime you are adding two, or sorry, sum of two cubes. Anytime you are adding two perfect cubes, it's going to follow this factor pattern here. A plus B times the quantity a squared minus ab plus b squared. The a's and the b's we'll talk about when we start looking at some of these examples, what those are going to be. A very similar one is called difference of two cubes. That's if you have two things that are perfect cubes being subtracted from each other. Then it's going to factor to this other one, the quantity a minus b times a squared plus ab times b squared. Notice both of these are very similar. There's just a few differences in the signs here and here, which signs you got. But otherwise, the a's and b parts are all the same. So just depending on what signs you have, it kind of switches a little bit. All right, let's try some of these out. On your note sheet, the first one wants us to factor x cubed plus 125. Notice this is cubed. It's not a quadratic one. It's a cubed one. So we want to figure out what's being cubed in both of these. The first one's easy. Right here, it's x that's being cubed. Okay, what number is being cubed in this second one is what we want to figure out. Now, some of you might be able to kind of just think about that and find it. If not, there is a way we can do it with the calculator. So let's pull up the calculator. And we're looking at that number 125. So if you want to find what number's being cubed, then do the cubed root of it. So if we find our cubed root on this particular calculator, if you hit your math menu, you can find the cubed root. So what's the cubed root of 125? It's 5. So 5 is the number here that is being cubed. So it's x is being cubed and 5 is being cubed. So we want to figure out which of these cube patterns do we want to use. Well, this one had a plus in between them. So we want to select this first one, or this middle one that says sum of two cubes. We're going to follow that factor pattern. So it's going to be, the factor pattern we're using says a cubed plus b cubed equals a plus b times a squared minus ab plus b squared. So what is our a and b that we're putting in here? In this case, this is your a, the x, and the b is going to be 5. So anywhere we see an a, put an x. Anywhere we see a b, put a 5. So what this is going to end up being is x plus 5 is the first one. Now we got a squared. So a is x here. It'd be x squared minus a is x and b is 5. So this will be 5x plus b squared. Our b in this one's 5. So if we take 5 and square it, we get 25. And there's our answer. All right, for tomorrow, why don't you guys see if you can try number 5 out, and we'll check and see what you get tomorrow on that one. All right, let's try another one. This next one, these ones are some of those perfect squares. We don't have anything cubed anymore. It's something squared. So let's use that perfect cube pattern, or square pattern. So what is being squared here? What number squared equals 49? 7. So it looks like the answer on this one is going to be a plus 7 times a minus 7. It's one of those ones. All right, let's try number 7. Now this one doesn't look like the last one. It actually has x to the 4th power. So can we do this one? Well, yeah, actually we can. Even though it's x to the 4th, we should still be able to use that pattern we did on the last one, where we said it's going to be a plus 7, a minus 7. The number being squared here is 9. So we can still do this one, but if we just put x plus 9 and x minus 9, we don't quite get to our answer here because this is x to the 4th power. So instead of just x and x, what we're going to do is put x squared and x squared. And now we have this factor. Now, remember on these ones, we do want to try to factor completely. So can we factor what's here anymore? This first one, no, I don't think we can factor that first one more, but does this one look familiar? Yeah, we've seen this one before. This is one of those difference of squares ones, again, that we just did on the last problem, we can factor the second one into two more terms. The perfect square being 9 here, square root of 9 is 3, so this would be x plus 3 times x minus 3. The first one, there's nothing we can do to factor that. So this would be completely factored now. All right, let's try the next one out. On these next ones, they want us to factor, and these ones are some of these quadratic ones, but notice it does, it's not x squared, it's x to the fourth. So what do we do if we got this? Well, what we can do, and this is on the back of your note sheet, anytime we're solving some of these ones and they're not quadratic, they actually have x to the fourth, is use the same type of technique. It's just that instead of factoring and just having x squared here where we just got x and x, if it's x to the fourth, it's going to split up as x squared and x squared. The other part still is the same. Your factors will still be what multiplies to c here and adds to b. So the only difference is you got to put squared and squared instead of just x and x. Let's go back and try this problem out then. So we know whatever we have here, instead of just being x and x, it's going to be x squared and x squared. Now to figure out the rest, you do what you've done before with factoring on these quadratic ones. What's going to multiply to negative 50 and add to negative 23? Well, in this case, it looks like negative 25 times 2 does that. So if we put in negative 25 and positive 2, that's how this one would factor. Now again, we want to check, does this factor anymore? Are any of these factorable again? This first one is. It's another one of those perfect square ones. So what number squared equals 25? 5 does. So we can still factor this one more as x plus 5 times x minus 5. Oops, sorry, x minus 5. This second one, 2, is not a perfect square, so that one we can't do anything more with. So this would be now factored completely. For tomorrow, I want you guys to try number 9 out. See if you can do number 9 for tomorrow. And then we'll finish off the rest of the notes then.